So, welcome student to the next class of Introduction to Nonlinear Optics and its application. Today we have lecture number 36. In the previous few classes we have studied this parametric amplification process, which is generated due to the presence of nonlinearity of the medium that we have learned. So, today we will going to extend that thing. So far we have learned how if I launch a field with frequency say omega p, which is called the pump, it can split into two different frequencies, omega s and omega I, which is namely signal and idler, and when they are propagating together there is a process so that they can amplify. So, this amplification process is generally called parametric amplification process. So, today we will going to see what happened if two frequencies are adding up and then generate a new frequency, which is a summation of that two frequency, and how these things going to amplify and what are the consequences of that. So, in the previous case and this case also, the process is essentially the parametric process. So, let us start with today's topic, and today we have one important topic, sum frequency generation under OPA. So, sum frequency generation we have already studied in the previous classes. So, the basic concept is known that if two frequencies are launched together, so there is a possibility that we will get a frequency which is sum over that, and this is entirely a nonlinear process. The nonlinear frequency mixing is there, but the field that will going to generate this sum frequency is going to evolve, and this evolution process is important. And as I mentioned, this is a parametric process and it will related to some kind of application. So, it is important to study, because in many cases we required a frequency, and frequency mixing can generate such kind of frequency, and we can from this frequency we can make some sort of laser with that particular wavelength. So, let us see what we have. So, optical parametric amplification for difference frequency generation. Here in this slide DFG is suggesting that it is difference frequency generation. The process is understood. Omega s and omega p are two input frequencies that we have launched to the system, and because of the optical parametric amplification, three different frequencies can evolve with the output, omega s, omega I and omega p. Here omega I is a difference frequency, namely it is called the idler frequency, and the process, the energy diagram or the energy process is also shown in the right hand side, that if a pump is launched into the system, then two different frequencies can generate. One is omega s and one is omega I, but the energy conservations are there, and the signal can be amplified because of this process, and this is the this amplification process is basically due to this optical parametric amplification, and also the idler will going to generate. So, in difference frequency the evolution of the idler is important, because we need to find out what is this difference, what is the frequency that is the difference between omega p and omega s that is launched in the input. Well, the scenario is slightly different for sum frequency generation as shown in this figure. In the left hand side the figure is almost same. This is a schematic figure of how sum frequencies are generated, that if I launch omega s and omega I, the frequencies of two fields containing omega s and omega I, then due to this optical parametric amplification process, one new frequencies one can expect to generate, and that new frequency is omega p, which is summation over these two frequencies. So, now the question is how this new frequency is going to evolve, and also the idler is there in the system. So, how the idler wave is there, that we need to find out. One thing you should note here, that here since I am generating the some frequency, the launched wave frequency omega s, which we call the signal, is strong. When we say the pump is strong, then that essentially means that there is no change over distance. The amplitude of this wave will not going to change over distance. Here we say the signal is strong, and the word strong means there is no change of amplitude throughout the distance. That means the field associated with omega s, if I write this field is E s, we will consider this as a constant. So, we have seen before that whenever we make one parameter or one variable constant in the coupled equation, then it is easier for us to solve that particular equation. So, here also we will consider that the efficiency of conversion of this pump to signal is relatively low. When the efficiency is small, then what happened, that a small amount of energy can pass from this signal to pump, and we can consider the signal to be constant. So, it basically helps us to solve the differential equation quite easily, otherwise it will be a cumbersome job to tackle with all the three differential equations which are coupled to each other. So, all these three differential equations, by the way, is already derived, and this equation are something like this. So, I am talking about the coupled differential equations. So, these are the equations I am talking about, but here we are using only two equations. Since pump is constant, so I am not going to, since signal is constant here, that means E s is constant. So, I am not going to take the differential equation related to E s. So, the first equation is the evolution of the pump, and second equation is the evolution of the idler. We know that this equation should contain another term which is e to the power of I delta k z, where delta k is a phase mismatch, but for this particular treatment we just consider that there is absolute phase matching. That means delta k is equal to 0. That is the condition for which I can write this kind of equation by just eliminating the exponential term. So, we are using this equation for last few classes. So, the process is exactly same. So, what we need to do to solve this equation when E s is constant, that we just replace E I from this equation, and in order to replace E I from this equation, or what we need to do, we need to make a derivative of this quantity. So, if we make the derivative of the first equation once again, then we have a second order derivative d 2 E p d z square. This quantity I kappa E s is constant because E s is constant in our case. So, this term will be here, and we have a derivative of this quantity which is d E I d z. Now, d E I d z, this term is in our hand, this, and we just replace these things here in place of d E I d z. So, when we replace this term, we will have a term like kappa p kappa I with a negative sign, because this I and this I will give a negative sign, and also we have E s mod square which is also a constant, and E p. Now, if I consider this term as delta square, because all these things are positive, so delta has to be a positive quantity, then we will have an expression like this. So, this is a well known expression. So, one thing we should mention here, that when we are dealing with the difference frequency, then there was a plus sign and the nature of the solution was different. So, in the previous class we try to find out how the difference frequency is evolving under optical parametric amplification, and that time we noticed that this equation, this sign was plus. So, we have a sec hyperbolic and cos hyperbolic kind of solution. The combination of these two as a solution we get. But here what we are getting is a sign solution because of this negative sign. So, that means somehow the EP, that means the pump, will going to evolve, but this evolution seems to be periodic in nature. Whatever the boundary condition if I put, then we find either it should be a sine, cos or combination of both, but there should be some kind of sinusoidal variation. So, once we have this expression, the next thing is to evaluate A and B as we have done in our previous class. So, first we try to find out what is my EP. So, EP at z equal to 0, that we need to consider to find out the boundary condition, and the structure is something like this. If you remember that I launch a signal with omega s, I launch a idler with omega I, and omega p is generating with the condition that omega p is equal to omega s plus omega I. That was the condition. If this is the condition, then we can see that this is z equal to 0 point and this is say z equal to some L point. So, the boundary condition suggests that at z equal to 0, there is no field containing the frequency omega p. That means, EP at z equal to 0 is 0. That is the mathematical description of the boundary condition that we have mentioned. Here, if I put this boundary condition, because EP at any z point or the solution of the EP is known to us. So, now if I put z equal to 0 in this equation, then we find that this term will not be there and only we have B, and this B is 0. That means, one part is readily eliminated when I put the boundary condition, and the boundary condition suggests that there is no pump field or the some frequency field at z equal to 0. So, our equation or the solution simply becomes EPZ is equal to A sin delta z. That is the solution we have, but still we need to find out what should be our A. So, again in order to find the A, the next boundary condition that we will going to use, and this is the same procedure that we have been using for last few classes, that for one condition we just put what is the value of the field at z equal to 0, and in other case we try to find out the derivative, because the derivative is proportional to the field of other frequencies, and we know what is the value of the field of other frequencies at z equal to 0 point. So, dEP dz at z equal to 0, which is essentially I kappa p Es Ei. So, this value at z equal to 0 is simply I kappa p Es Ei 0. So, the condition here that we have taken is the field idler field at z equal to 0 is not equal to 0, as I mentioned, because we need to launch some idler at the input to generate the frequency at omega p, which is a sum over two frequencies. So, this value we have taken as, since this is non-zero value, so we have taken Ei z equal to 0 is simply Ei 0. This is the case where we use these things. Now, we know what is the value of EP at z point. So, we make a derivative of that. So, when we make a derivative of that, we will get A delta, and once we get A delta, that should be equal to that quantity. That means, A delta has to be equal to this. So, we will finally get what should be the value of A. So, A finally we find A should be something like this, I kappa ES EI 0 divided by delta. Now, next I put the value of delta, because if you remember, delta square was kappa P kappa I mod of ES square. So, root over of delta is root over of kappa P kappa I and ES. Mod of ES square can be considered as a completely real quantity. So, that is why when I take a root over of that, so I can say this is simply ES. So, that means we are not considering any kind of phase at the input, or the even if there is a phase, we can call this phase as 0, and respect to that phase we are measuring other phases. So, ES, whatever the field we have at the input, is having some kind of phase which we consider the reference. So, we consider this as a 0. So, then this becomes simply a real quantity. So, when we do that, then this ES will cancel out. By the way, this assumption or whatever we are doing here is we can say without any loss of generality. So, there is no harm to take this kind of consideration. So, we can always do that. So, A finally after doing this, A become I root over of kappa P divided by kappa I E I 0. So, EP finally I find that EP is something like this, root over of kappa P kappa I E I 0 sine delta z. So, that means it is evolving, and it is evolving as a sine function, and at z equal to 0 point this quantity is 0, all the boundary condition is valid. But at the same point we need to find out how the idler is evolving, because pump is constant. So, pump is not going to change, but this signal is constant here. So, signal is not going to change. So, signal is feeding these two fields, pump and idler. So, once pump and idler are fed by this signal field, so both these things will going to evolve. So, we need to find out how EI is also evolving. So, in order to find out the evolution of EI, we will not going to solve again everything, rather we just use the relationship between EI and EP, because we know that dEP dz, this is again our fundamental equation or the mother equation, is I kappa P, then E of S and E of I. That was our expression. So, EI from here I can write it is 1 by I kappa P ES, which is this quantity, and dEP dz. Now, dEP dz is one can figure out, because EP, the functional form of EP is known, and if we do that dEP dz, then I find dEP dz is simply I divided I root over of kappa I kappa P kappa I EI 0, then delta cos of delta z, thus derivative of this quantity with respect to z. Once we have this quantity dEP dz, then we can just put these things and we can figure out what should be the value of EI. So, dEP dz is this quantity. So, I kappa P kappa I E 0, and I put this quantity which is nothing but delta. So, when I put this delta, so this delta this quantity kappa I will cancel out, and kappa P become I kappa P, and ES will be there, EI 0 will be there, and cos of delta z is there. So, from here we can find out what is my EI, because EI is this quantity multiplied by whatever we have, this thing I now replace with I kappa P ES I 0. So, finally, we come with this solution, which is EI 0 cos of delta z. You can see that again the boundary condition is satisfying, because we know that EI at z equal to 0, it EI 0, and if you put this z equal to 0, then cos of 0 becomes 0. So, we have EI at z equal to 0 is simply EI 0. So, these two expression we have in our hand, which is EP and EI. So, EP will evolve in this way, EI will evolve in this fashion. So, now after having this expression in our hand, so we now calculate. So, these are the two expressions we have, these are the two expressions we have. So, we now calculate what is the value of the corresponding powers, because we always present the thing in terms of powers. So, the power associated with the electric field EP can be simply written as this: PP is equal to IP multiplied by A. IP is the intensity and A is the area. So, intensity multiplied by area is the corresponding power. So, intensity again can be represented in terms of mod of field square. So, which is this expression. We are using this expression several times. So, by that time you are familiar with this. So, whenever we have intensity, we can replace this intensity in terms of field, or whenever we have field, we can transform this field to intensity, because intensity is a measurable quantity, so as the pump. So, we always try to find out in terms of intensity or power. So, this quantity EP mod of Z square we know, because these are the two solutions that we have generated through this coupled equation, and when we put this thing in this expression, this becomes half epsilon 0 n NPC. This quantity is as usual, because this is already there, and mod of EP square means square of this quantity, or this multiplied by the complex conjugate. When we make the complex conjugate, this I term will not be there. So, we have kappa p k I mod of EI 0 and sine square delta z. In the similar way, I can also find out what is my PI, that means the power of idler at z equal to 0 point. I am just taking what is the value of z equal to 0 point, because when I because I know that this is the value at z equal to 0 point. So, just to replace these things from this equation, I just want to find out what is the ratio of pump power at any point z to the idler power at z equal to 0. What is the ratio between these two? So, when we do, we find that this is simply this, and now this is cos theta. So, if I want to find out what is my Pi z, we can find it out. So, it is I 0 A, which is half of epsilon 0 C n I, and then E of I mod square. So, this term will be simply become E I 0 cos a square delta z. So, it will evolve, the power will evolve like cos a square. So, the ratio between these two is having this. When you make a ratio, this divided by this, so half epsilon 0 n, this term will cancel out, np kappa p will be there, in the denominator we have ni kappa I, which is also there, I will also be cancel out, this term are cancelling out each other. So, we will have sine square delta z here. So, this is the ratio of these two things. Why I am taking the ratio, I will show in the next slide. So, once we have the ratio of PPZ and PI at 0 point, then this ratio can further be modified, because kappa p whatever. So, let us write what we had. So, in the previous slide, PP divided by PI 0 z, this was kappa p NP divided by kappa I Ni, and then there was sine square delta z. So, this quantity if I replace with this, then we find that kappa p n p is d omega p divided by c and kappa n I is d omega I divided by c. So, their ratio simply became omega p divided by omega I. Sine square delta z term will be there as usual. So, the next thing is, if I want to find out, because this quantity is now varying with sine square. So, that means the ratio of this quantity is varying sinusoidally. Now, if I consider what is the maximum power transfer. So, what is the maximum value of this quantity? So, readily we can see that the maximum of this value will be when this quantity is 1. So, sine square delta z is 1. So, when sine square delta z is 1, so we can say this value is maxima. So, that means the maximum power at pump, and this quantity in terms of the idler power at z equal to 0 is this multiplied by some parameter omega p and omega I. This is the frequency of pump and idler. Now, the number of idler photon per unit time per unit area that is moving can be represented in terms of power and energy, we know that. So, power at 0 point divided by z equal to 0 of idler power divided by the total energy can give you the total number of idler photon. Also, we can find out what is the pump photon, number of pump photon. So, now idler photon and pump photon are related to this expression, and now if we look carefully, if I now make a ratio of these two things, then we find interesting things, that if I say the number of idler photon that is generated, if this is equal to the number of pump photon, then this condition is same as whatever the condition we figure out regarding the power transfer. So, that suggests that if I now plot these two things together, then we can find that the idler power and pump power can exchange the energy, and when total amount of idler power. So, this is the idler input idler power, and now it is reducing and reducing to 0 value, and the pump idler power, the pump power is now increasing to the maxima. So, now there is a power exchange between the idler and pump, and if this ratio is this, that means the total amount of idler photon is now totally converted to the total number of pump photon. So, that means there is a power conversion, and this power conversion is periodic in nature. So, today we will like to conclude here. So, we have learned an important thing today, that some frequency generation under optical parametric amplification is possible, but in some frequency generation process we find that like difference frequency generation, the signal is evolving as well as the idler is evolving over jet monotonically. But here we find that this monotonous evolution is not possible for pump. So, pump means the sum of these two frequencies. So, that will going to evolve periodically, and there is energy exchange between idler photon to idler wave to the pump wave, and we can suitably have the value of jet for which we can get the maximum pump power, that means the sum frequency power. So, with this note, let me conclude here. So, thank you for your attention, and see you in the next class, where we are going to study more about the optical parametric amplification and optical parametric oscillation. So, see you in the next class, and thanks.